Okay. We're going to go ahead and get started. So far, mostly what we've been talking about has been math. I know you guys love math. But anyway, today we are going to move into chapter 3, which is a little bit more of chemistry rather than just math. Okay. Now, I'm planning to move through this material fairly quickly right now, mostly because these are concepts that you are already sort of familiar with, okay, just by being alive, right? If we start going too fast and you're confused, let me know. We'll slow down. But anyway, I don't want to spend a whole bunch of time talking about things that you're just like, well, yeah, of course. Okay, why are we talking about this? Okay, so, all right. So properties of matter. Properties of matter. So we need to establish what is matter. Matter is anything that has mass and takes up space. If it has mass and takes up space, it is matter. Okay. You are matter. Everything around you is matter. Okay? The desk, the book, the air you're breathing, it's matter. Everything is matter. We're going to have some definitions here. First one is substance. Okay. What is a substance? What is a substance? It can be a liquid or solid, but you can have other things that are liquid and solid that aren't substances. I'm looking at a great sentence right now in the book. On page 70. Recall.
Substance always has the same composition properties.
Yeah. Matter with a uniform and unchanging composition is called a substance. Okay. So if everything throughout this sample is the same, it's a substance. We'll get to when it is not a substance in just a little bit. Anyway, so this is what I mean by, you know, this kind of material. The states of matter. Who can tell me the states of matter? Solid, liquid, and gas. Those are the three most common. There are other ones. One that Bill Nye says. Not sure. I know he says that inertia is a property of matter. Anyway, so yeah, you're familiar with solids, liquids, and gases. You're actually familiar with the fourth most common, plasma. You may just not realize it. You ever seen a neon sign? That's plasma. Okay. Fire, that's plasma. Okay. So you're familiar with it, but it's not one of the common ones. Anyway, solid. Okay. It has its own definite shape. You take a solid and you put it in a container, it stays the same shape. Okay. Yeah. It has atoms or molecules that are really densely packed together. And yeah, you guys know what a solid is. Liquid. Liquid is still fairly dense. In most cases, it's not as dense as the corresponding solid. There are some exceptions, which we'll get to. But because it's not as dense, these atoms or molecules can flow over each other. Okay? And that's why we have the properties of liquid that we do. Okay? If you take liquid, so if I have my water bottle here, okay, that water takes the shape of its container. Okay? Takes the shape of its container. That is not the shape that the water was when it came into this bottle. Okay? It came in a much narrower stream, but it filled the container. Because that's what liquids do. Okay? Liquids also tend to settle at the bottom of their container, which is something that differentiates them from gases. Okay? So it doesn't have to necessarily completely fill the container. Obviously, you can see the water is just down there at the bottom at this point. It hasn't filled the container. But you can pour it, and moving on to gases. Now, a gas is, it's interesting because we call liquids fluid, but we also call gases fluid. It means you can pour them. We will, maybe we'll have time on Friday. I can show you proof that we can pour a gas. We don't have time to do it today, but it's a pretty cool demonstration. We prove that even though it's a gas, you can actually pour it down a ramp. So it's a cool demonstration because it involves fire. So anyway. Okay. So gases, you can pour them. They take the shape of their container, but unlike liquids, they fill the container. Okay. So if you think about it, if you have a balloon, the gas, the air in that balloon doesn't settle on one side. It fills the entire thing. Okay. Gases fill their containers. Okay. See, that's super easy. Let's move on. Okay. Physical properties. Every substance out there has physical properties, all right? And as it says, if you're following along, we've moved on to 73. So a physical property is a characteristic of matter that can be observed or measured without changing the sample's composition. Okay? So you're not changing anything about this, you're just observing it or measuring it. So something, well, there's a whole table here. I don't know what it is about last period, but they just always make so many announcements. Anyway, so color, that's a physical property. Okay. You can observe color and it doesn't change anything. When you look and see, oh look, that chair is red. That doesn't change the fact that the chair is red. It doesn't change anything about it. Okay? You're observing it without changing it. The melting point. Okay? We can heat something up to the point where it melts. And you might think, well, that's kind of a change, but you're not changing anything about the substance itself. You've just changed what phase of matter it is. Okay? So we can observe and measure the melting point or the boiling point. We can measure density and things like that. So physical properties, we can observe them or measure them without changing anything about the material that we're working with. Okay. Now, this also gets into extensive and intensive properties. Extensive properties depends on how much you have. Okay, so we can measure the mass. Okay, for example, these two weights. Okay, we know that this one is 20 grams. Okay, we put that on a balance. It will say 20 grams. It doesn't change anything. Now this is the same material. It's made out of the same stuff, but this happens to be 50 grams. So that is an extensive property. It depends on how much you have. Okay. Intensive properties, it doesn't matter how much you have. So things like, well, density at a certain temperature, color, okay, things like that. So if it changes based off of how much you have, that's extensive. It doesn't change, intensive. So those are physical properties. That's pretty straightforward. All right. What we are most interested in, really for the whole of this class, are the chemical properties of that. Okay? That's where things become interesting in chemistry. Okay? When you can mix two things and get some sort of change. Okay? How these things mix and interact is a chemical property. Okay? The official definition that they give it in the book: the ability or inability of a substance to combine with or change into one or more other substances is called a chemical property. Okay? Like I said, if you can mix things together and they change, okay, how they change or don't change, those are what we call chemical properties. Okay? So it gives the example of copper. Okay. Now, pure copper in its normal state is a brown, okay, shining brown. But if you leave copper outside, it changes to green. And it's not because it got dirty, it's because the copper is reacting, turning into copper oxide. So it's no longer just pure copper, it's mixing with oxygen. If you are familiar with the Statue of Liberty, Statue of Liberty, when it was first put up, it was brown because it's made of copper. But over the years, it turned green, copper oxide. Okay? So, chemical properties. All right, let's keep moving. Let's talk about changes. Because, like I said, when things change, that's when things get interesting. Okay. Now, just like we had physical properties and chemical properties, we can have physical changes and chemical changes. Okay. As it says, if you can alter the substance without changing its composition, it's a physical change. Just like the physical properties, when you observe them or measure them, you don't change what it is. Okay. So if here we have a little Post-it note made out of paper. Okay. We can observe the size of that Post-it note. Okay. But look, I can change the size. Okay. So I've changed the size, but it's still that same green Post-it note. Okay, that's a physical change. Chemical changes, well, just like before, something is changing materials. Okay. Here we have a little pocket lighter. Okay. in there, we have chemical. In this one, I believe they're using butane. Okay. Anyway, it's clear. It's a liquid because it's under pressure. But, okay, that is a chemical change. Because what's coming out is no longer butane. Okay? We're getting carbon dioxide and water. And that heat release is what gives us the flame. Okay. So, chemical reaction. Now that is one possible chemical reaction. There are literally millions of different ways that chemicals can interact and change. Okay. And the book lines out some ways that you can tell. Things like a color change. You get bubbles, sometimes that does. The problem is sometimes it doesn't really look like anything happened. Sometimes you can mix two clear liquids together, get a chemical reaction that is still a clear liquid. Okay. So you kind of have to know what's going on. Anyway, this next thing is absolutely one of the most important concepts that we will talk about in chemistry. Super, super important, but it's not overly complicated. Okay? And it's called the conservation of mass. And basically what it means is you can't create or destroy mass. Okay? If it's there at the beginning of your reaction, you have to account for it at the end of the reaction. Okay? And if it's present at the end of the reaction, you have to be able to account for it at the beginning. Okay? So, for example, with the lighter, we've got butane. Okay, that's the chemical composition of butane. Doesn't matter if you know that or not. And I said we're getting water and carbon dioxide. Okay. There's a problem. Is there any oxygen in butane? No, there's no oxygen in butane. So I've got this element here that I didn't have at the beginning. Where does that oxygen come from? Yeah, it's the air around it. Okay? There's plenty of oxygen in the air to support that combustion. Okay? Now, granted, this also is not balanced, but we'll talk about balancing equations later. Okay? So, that's what we mean by conservation of mass. Okay? Also, balancing makes a difference too, because we only have 2 atoms there, we end up having 3 there, so that's why we have to balance. Okay. But anyway, we can't create or destroy matter. Now, at the very end of the year, we'll talk about examples of when that does happen, but for now, let's just assume that we can never create or destroy matter. Okay? And so the law of the conservation of mass is just that the mass of our reactants, which are over here, has to equal the mass of our products, which is over here. Okay. So if you started with 532 grams of total reactants, you must have 532 grams of products. Okay. So just as an example, if we have 532 grams of the butane and the oxygen, and these numbers are totally made up, this is, probably not at all accurate or whatever. But let's say we had, 210 grams of water. How many grams of carbon dioxide did we get? How would we do that? How would we figure it out? Yeah, we pull out our calculator, because remember, calculators are great in this class. Okay. Okay, that's fine. So for this, you can do this on paper without troubles. But we put 532, we subtract 410, and that gives us 322 grams. Okay. So whatever you have at the beginning, you have to have at the end. For conservation. Okay. There is another example problem of that on page 78. It talks about mercury oxide powder. So mercury oxide is, well, it's a combination of mercury and oxygen. They're reacted together. And it's a red powder. But if you heat that powder, it actually releases the oxygen into the air, and you're left with pure mercury, which is a silver metal that happens to be liquid at room temperature. Liquid metal at room temperature. Okay. So we said we've got 10 grams of the mercury oxide, and we heat it. And what we're left with, just the liquid mercury, is 9.26 grams. So we want to know, well, what is the mass of the oxygen that was released? We subtract. Okay. We get 0.74 grams. Okay. Does that make sense? If you start with it, you have to have it at the end. There is no other option. At least at this point. And the only time that there will be another option is when we get to chapter 24 at the very, very end of class. Okay. So you start with it, you have to finish with it. There's no other option. Okay. Now, this wasn't always widely known. People didn't necessarily understand that. Take, for example, if you're burning a candle. Okay? The candle looks like it's just disappearing. Okay? But it's not. It's just being changed. Okay? When you burn that candle, the waxes and everything inside the candle are being converted into simpler molecules that are released in the smoke. But if you are able to capture all of the smoke and all of the carbon dioxide and water that are released through combustion, if you can capture all of those, at the end, the mass that you have will be the same as the beginning mass of that. Okay? Nothing has just magically disappeared. You have to account for it somehow. Okay? So that is, well, as it says, The law of conservation of mass is one of the most fundamental concepts of chemistry. Okay? So many of the things that we do depend on this being true. We use that in order to do calculations and figure out things. So, okay. Now let's move into section 3. See, we're just flying through this material today. We will not always go this fast. Okay. Trust me, I know that it seems like we're just throwing a whole bunch at you today. Most of the time we'll go a lot slower than this. Okay. Anyway, so section 3, and this is going to be the last section that we actually work on and that we have to go through today. So mixtures, everything that we've been dealing with so far has been a substance. Okay, our butane. Okay, in there, that's all butane. It's just that's what it is. Okay? It's a substance. Now we need to talk about what happens when we take things and mix them together. So if we have 2 or more pure substances that we mix together, we call that a mixture. Okay. Now, if you look at page 80, at the bottom, it shows 2 different examples of mixtures. Now, one of them is this lovely filling in a tube. Okay. And it's a silver filling, which is a little bit of an older technique. Some places will still do them. But most places will do the white colored fillings now that look a little bit nicer. Anyway, there are multiple different metals in that filling. But you can't just look at it and say, oh yeah, that part is silver, because it's mixed. But then next to it, we have that salad dressing. When you look at that, you can see all these little bits and pieces of the spices and flavorings and whatnot. Okay? So that one you can see these different pieces. These are the 2 main types of mixtures. Okay? And we have specific names for them. We have heterogeneous and homogeneous. Okay. So heterogeneous would be the solid dressing. If you can look at something and see the different pieces, that's a heterogeneous mixture. Now it's still a mixture, everything is all mixed together, but I can see these different pieces. Okay. The filling with the metal, where you can't tell what is what, that becomes homogeneous. Okay. Homogeneous means it has a constant composition throughout. Okay. If you pull a sample of a homogeneous mixture from here and another one from over here, they're going to be the same. They're going to be the same stuff. It's going to be the same properties. But with that salad dressing, if you take a sample from over here, there's a good chance that you're going to get different things. Okay? That is the difference. If it has a constant composition, homogeneous. If it's not, it's heterogeneous. Okay. We have another word for homogeneous solution or mixtures. It's called solutions. Okay. When you have two things mixed together that you cannot tell the difference between what you've mixed, we now have a solution. Now you're familiar with different solutions. In fact, well, there's several different solutions that you're probably familiar with on page 81 in that table. And even though we're most familiar with liquid solutions, they can be all sorts of different things. It gives the example of the air in a scuba tank. Okay? That's a solution, including the air around you. Okay? So most of the air around you is made up of nitrogen, but we also have oxygen and several other things. Can you look at the air and say, oh, well, that's nitrogen there and this is oxygen here? No. Okay, it's a solution. It's a homogeneous mixture. You can also have gas and liquid. So if you have oxygen and carbon dioxide that are dissolved in seawater, or carbon dioxide in a soda, okay, carbon dioxide is dissolved in the soda, that's a solution. Okay, now, granted, once you open it, a lot of that will escape in bubbles, but you still have some of that dissolved in there until you leave it open for a long time and it eventually will, or at least almost all. So, liquid and gas, so it talks about like humid air. Okay, so if you have a whole bunch of, Utah's a pretty dry state, but if you go to the coastal areas anywhere, some of you who aren't from Utah are probably more familiar with that. You get a lot of water vapor in the air. Okay, once again, you can't see the water vapor. Okay, it just mixes with the rest of the air. Liquid. I don't love that example that they give with the fresh water mixing with seawater. I think it's kind of a weird example, but it works. Also, if you try to think of a good example that you might be familiar with, like, let's say you take a drink and you put water in it, okay? And then it mixes together, okay? Like if you have a sports drink like Gatorade or something, and maybe it's too sweet for you, so you put water into it, that thins it out a little bit, that becomes a new solution, okay? You're mixing two liquids together. Solid and liquids. Salts dissolved in water. Okay. If you are in the kitchen and you have to cook noodles or rice or whatever it is you're cooking, a lot of times you'll put salt in the water. Okay? It adds a little bit of flavor when you're cooking, and it dissolves. Now, obviously, when you very first put the salt in, you can see the difference between the salt and the water. But once it dissolves, you can't see. Okay? And then solid talks about metal alloys. Alloys are a mixture of two metals, much like that. So different solutions.
Also, is it like the solid, is it like two metals mixed together?
Yes.
Like melt and mix?
There are different ways that you can mix them together, but often they do melt them, just kind of depending on if they have similar melting temperatures and things like that. But yeah, or even like steel. You take carbon and iron, you mix it together, okay? You get steel from that. Interesting thing, I believe it was the Vikings. They used to take the bones of like animals that had been killed and mix it in with their iron when they made their blades. And they knew that it made it stronger. Really, it was the carbon from the bones, but they thought it was like the spirits of the animals imbued themselves into the blade. Really, they were just making primitive steel. So, well, if you make a blade, you're going to make it out of steel.
Well, yeah.
But yeah, they were making primitive steel. Okay. So how do we separate mixtures? It's often a question in chemistry. Because a lot of times you'll do a reaction and you want one of the things, but not everything else. Sometimes it's heterogeneous, sometimes not. So sometimes we need to know how to separate these things. Okay. Now, heterogeneous is often a little bit easier because since you can see the different pieces, you can take what you want. You can filter it. So like if you have a solid and a liquid, it is possible to mix two liquids and get a solid as the reaction. We'll talk about why that is later on. But if you do that, then you filter it. You either collect the liquid if that's what you want, or you collect the solid if that's what you're interested in. Filtration is a great option. They even sometimes, depending on what you're working with, they can have special filters that will collect what it is you're interested in. So when I was in college and I was working with DNA and RNA, they have special filters that you pour your mixture through, and all of that DNA will sit in the filter until you rinse it with the right thing. And then that pushes it all out. So you filter everything out that you don't want, and then you send in the rinse, and that pushes the nucleic acids that you want. It's actually pretty interesting. So filtration is very useful. Sometimes it's as simple as just, like a piece of filter paper which holds solids. Other times it can be very complicated, like the nucleic acid filters. So, if it's not heterogeneous, if it's a solution, it's homogeneous, we need to come up with some other options. One thing that we can do is called distillation. Distillation is often associated with the making of alcohol.
Is that we like set it for like years?
Okay. Basically, what we're doing, at least in, we'll go with the making of alcohol, because that's an example that most people are at least a little bit familiar with, whether or not, well, none of you are actually old enough to drink, so, but whether or not it happens in your home. So, essentially what we have, we've got this reaction vessel, and this is where the yeast actually makes the alcohol. Okay? Alcoholic beverages are made by yeast, microorganisms. Okay? Does that surprise you? Anyway, so you give yeast some sugars. Usually that comes through grains and stuff like that. And we get alcohol, but then it's also mixed in with a bunch of water and things like that. So we want to get the alcohol out. So what we do is, see my lovely fire there? We heat it, okay? But we have this covered And all of the evaporation has to go through this tube, which we call a condensation tube. Okay. And it drips out into a different container. So the reason why this works is because alcohol evaporates at a much lower temperature than water. Okay? So the alcohol leaves while the water is still in here, and obviously the solids stay as well. So we are separating this mixture using distillation. Okay? We're taking advantage of the fact that alcohol evaporates at a lower temperature than water. Now, if you continue to heat it, then obviously you're going to start getting water through. You will get a small amount of water that comes through anyway, but it greatly purifies your product. Okay, that's distillation. The next one it talks about is crystallization. Now, this is an interesting one. Some substances are able to form crystals. Okay? Basically, what happens is they start to build on each other into a solid pattern. Okay? And we can take advantage of that to get something out of solution. Now, this might be something that you've even done. Any of you guys familiar with rock candy? Okay. That's really what rock candy is. It's crystallized sugar. So the way that you make rock candy, and you could do this at your home, you have to boil a whole bunch of sugar in water. Okay. Now, the fact that you're boiling it allows more of the sugar to dissolve. And so you get that, and then you put a piece of string or stick or something in the water as it, cools, and those sugars will start to stick to that stick or string or whatever you're using, and they build this crystal. So you're pulling the sugar out of the water. Okay? So you're separating them, and that allows you to pull the sugar out of the mixture by crystallization. Like I said, that is something that you could do at home if you're interested in doing that. You can look up the exact ratios that work better with the water and the sugar and all that. But yeah, ask your parents though before doing that. Just because I don't want angry emails. Anyway, so there's that. And then there's sublimation. When we talk phase changes, we'll talk sublimation, but it's actually possible for things to evaporate straight from solid. They can go straight from solid to gas. That's the triple point. We'll talk about that. That's a lot like distillation, except we're going from solid to a vapor. And then chromatography. That's pretty much what I was talking about with the nucleic acid filter. Chromatography is really sort of like filtering, except instead of just separating by size, we can separate by all sorts of different things. We can separate by whether or not something is polar or non-polar. We can separate by size. Also, one useful thing about chromatography is we can put multiple different things together in a mixture, and chromatography will actually separate them all individually if you use the right method. You can put 5 different things, and you do the chromatography, and it will, the first one will come out, and then a little bit later, the second one will come out, the third, and so on. It's a very, very useful tool. So, okay, so that's the end of section 3, and as promised, we're not going to go into section 4. You know, we've thrown a lot at you today, but most of it up until, you know, section 3, you probably were fairly comfortable with as far as, yeah, this is a solid, this is a liquid. You guys can identify those. So we're going to stop there. As I'm sure you're expecting, I do have an assignment for you. So that's just kind of the nature of this class. There's homework. So, but I'll put that up on the board for you, and I'll give you the rest of class to start that.